As I told you in the last class, we are going to solve a boundary value problem. How we can solve it using whatever we have learned. Okay, and I'm going to illustrate this with the example of what's called extension torsion inflation in a beam. All right, so, or maybe it's a tube. So here is your tube. And suppose that this is your z axis, and then you have x and y. So in order to extend a tube, we all know that we have to apply axial force to it. If you want to twist it, we have to apply twisting moment, and if you want to inflate it, you'll have to pressurize it from inside. So this can be imposed by applying torque, this by applying axial force, and this one by applying internal pressure, for example. So if you view this as a 3D body, if I view the beam as a 3D body, then we had discussed that the equation that is to be solved is the LMB equation, which is divergence dot P plus the body force is equal to acceleration. Okay, now suppose that body force is not present here. See, you may be applying pressure from inside, but that's not a body force. Body force acts at every point in the body, and it has the unit of force per unit volume, whereas pressure has a unit of force per unit area. So it's not a body force. So we are going to drop this, assuming that gravity is can be neglected and there is no other body force. And also suppose I want to do statics. So I can also drop this term for statics. So the equation reduces very simply to this. And then you have to think of what boundary condition to apply, isn't it? So it has four surfaces. So you have z equal to 0, comma L. So supposing that the length is L, the two end cross sections, and then big R equal to big R1 and big R2, the inner and outer lateral surfaces. So these are the four surfaces. Okay, now, so here we want to do it in a Lagrangian way. All right, so the outer surface is, as you can see, is traction free. So we can say that the first pk stress tensor big P into big E, sorry, E times E big R. So E big R is the radial vector, the undeformed coordinate. In the undeformed configuration, whatever is the outward normal, because you see after deformation this could become like this, we don't know, right? It could become something like this, and then the outward normal here is pointing this way, whereas initially in the undeformed state the outward normal is perpendicular to z-axis, and in Lagrangian we have to work with the undeformed normals. So this is going to be 0 for big R equal to big R2, right? That's the outer surface. What about the inner surface? So what we're applying is a pressure, and pressure, as you all know, it's the Eulerian thing. So pressure fixes the Cauchy traction component, which in this case is actually sigma, and let us say the so sigma into n, where small n is the deformed normal, and dot with the deformed normal. Well, actually it's always in the direction of normal, so this is equal to minus p into n. Okay, for big R equal to big R1, the inner surface. But how do I convert this to Lagrangian? So we have already seen this, so we can write, so sigma n is so basically sigma small n d small s is minus p small n d small s, but this is also equal to big P into, you see what is the undeformed normal? That's radial again, but the outward normal is pointing in the minus ER direction. Can you see this? The undeformed outward normal for the inner surface is pointing towards the axis of the cylinder, whereas the radial vectors are always pointing away from the axis of the cylinder. Therefore, I get a minus sign here. So minus P E big R D big S. And then here I can use the surface transformation rule, and it becomes minus P into det F into F inverse transpose, and then again the undeformed outward normal, which is minus E big R D capital S. So when you compare the first one with the last one, we get P E capital R is equal to minus P det F inverse transpose into E capital R. Okay, so that's for the inner and outer lateral surface. Now what's going to happen at the two end cross sections? So this depends on how exactly this is being deformed. So are we applying kinematic boundary condition, or we are applying, let's say, traction boundary condition? Okay, so assuming that it's a kinematic boundary condition, let us say it's kinematic. for z equal to 0 comma L, then we could, for example, simply take the end cross sections and displace by some amount delta along the axis, keeping the radius fixed. That could be one kind of kinematic boundary condition. But you see that we have to also apply torque here. So how can we apply torque? We have to then do equal and opposite rotations, right? So that it twists. Okay, so suppose that's also kinematic. That means I am rotating the two ends by theta, by an angle theta. So what can you say about the displacements of points on the two cross sections? For example, what will be u when it's big X, big Y, and then big Z is equal to L. So suppose the rotation is by omega naught and the axial movement is by delta. So due to this big omega naught, it's going to rotate, isn't it? The points, so if you look at a cross-sectional view, any point at an angle having undeformed coordinate big theta is going to move to such that it becomes big theta plus omega naught, isn't it? So it's simply rotating. So u is then, or maybe the position, you can say small x, is then the undeformed radius, let us say big R, into E big R, but E big R for big theta plus omega naught. See, the ER is different for different points. If you again look at the cross section, then over here ER is pointing like this, over here ER is pointing like this. It's always radially outward. So I have to take ER not of the original. Original is ER of big theta. So any coordinate, either you write it as big X, big Y, or you can write it as big R, big theta in cylindrical coordinate system. So the ER is not of big theta, but of big theta plus omega naught. So this just takes care of the displacement in the cross section. But then you have to also add to it the axial movement, isn't it? So that's going to be plus L plus delta Z E Z. Likewise, for the other cross section, it's going to be small x, again for all big X, all big Y, but Z equal to 0. So that's going to be big R, E big R, theta, but here minus omega naught because it's going to be rotated in the other direction, plus minus delta, or maybe if you are Yeah, there are two ways to do it. One is that you apply rotation and displacement at both the cross sections, and the other is you fix the cross section at z equal to 0 and apply rotation and displacement only to the cross section at z, isn't it? But here I'm showing it when you're doing it for both. So in that case, this becomes plus minus delta Ez. And as I told you, this is case 1. In case 2, if it is fixed, then it is going to be small x, big Y, and then at z equal to 0, then that is simply big R, E big R of original E big R only, at theta only, plus 0. Okay? Where this big R is square root of big X square plus big Y square, and this theta will be such that tan of this big theta is big Y over big X. That's how you transform from Cartesian coordinate system to cylindrical coordinate system, isn't it? So this is the boundary condition, and then you have to solve it, right? Now, of course, we can't solve this problem analytically. You just have to now go to computers and think of solving it. But let us say I want to do a very specific case of this problem, which is axisymmetric and axially homogeneous case. That means the deformations that are happening are such that they are not dependent on big theta. So axisymmetric, this means no dependence on big theta. Okay, and this means no dependence on big Z. So see, we are sort of trying to use cylindrical coordinate system. So for cylindrical coordinate system, the undeformed coordinate will be big R, big theta, and big Z, which is going to change to small r, small theta, and a small z. Okay? Now let us see how things are going to simplify if it's an axisymmetric and axially homogeneous case. And you see, whenever you have axisymmetric problem, no, it is best to use cylindrical coordinate system, because in that coordinate system, many of the equations get trivially satisfied, as I will also demonstrate to you. Okay, so let us think of using cylindrical coordinate system for solving this axisymmetric problem. Okay, so if it's an axisymmetric, what can you say about small r? So small r is the deformed radial position of a point which was originally here, big R, big theta, big Z. So small r, see, in general will be a function of all three, big R, big theta, as well as big Z. But now with axisymmetry, what do you think? So think of a cross section and here are all the points having that constant big R. And if I want the deformation to be axisymmetric, then all these points must go to another radius but all the same. If they have the same original radius, then they must be having the same deformed radius also. So the deformed radius must not be a function of big theta if it's an axisymmetric, isn't it? So that's what I have to say here. So if it's an axisymmetric, I would have to say that it is just a function of small r, big R, and big Z. But we are also talking of axially homogeneous. So what I mean to say, if this is the beam, then all the radial radiuses, the cross-section radius along the axis, they all must shrink or expand by the same amount. So the deformed radius, these ones, small r, must not depend on the axial coordinate, big Z. If it depends on the axial coordinate, then it becomes axially non-homogeneous, right? Then it's going to become something like this. This is just one example. So that means I further want to say that this is just a function of big R. So this is due to axisymmetry, where this is due to axial homogeneity. Okay. Likewise, what can you say about small theta? So small theta in general is a function of big R, big theta, and big Z, all three of them. But due to axisymmetry, what would we be able to say? Will it be a function of big theta, or it will not be a function of big theta? So maybe let us get back to this case later on, because this is a bit difficult one. Now think of a small jet. So that's also in general a function of big R, big theta, as well as big Z. So for the case of axisymmetric and axially homogeneous deformation, what do you think? What should it depend on? Any idea? What can you say about the dependence on big theta? So think of a cross section having same big Z value for a given cross section. Let us say over here, which I am drawing here. So it has the same big Z value, right? Every point has same big Z value. And then here are the points having different big theta. Now, if this depends on big theta, this Z, then can you see what will happen to the cross section if it depends on big theta? The cross section will suddenly not be planar, isn't it? And one is for sure that it is going to become, it's not going to obey axisymmetry. If it becomes a function of big theta, then it's not going to be axisymmetric, right? Because what does axisymmetry mean? If you rotate the deformed cylinder about its axis, you see the same thing. That's what it means. If you rotate the deformed cylinder about its axis, it will feel like you are having the same deformation. Now, if this small z is a function of big theta, here it's a different and here it's a different. Let us say here it is 1 and here it is 2 and here it is 3. So if you rotate by, let us say, this angle, which is 20 degree, Then over here the value will be 3, here it will be 1, so it has changed, right? So when you look at it, it won't look the same. So therefore there is no dependence on theta here for sure. That's due to axisymmetry. Now what can you say about dependence on big R? What happens if there is a dependence on big R? So different radial points have different small z. So again, think of this cross section, and here is all the lines having same big R, and then here is another line having different big R.
Axial homogeneity will not be followed in this case.
Well, let us see, if they undergo different z value, what is going to happen? Just think of what happens to the cross section.
It will no longer be planar.
Plane section.
Exactly, the plane section will not remain planar, isn't it? So we want to avoid that situation because that's a bit difficult situation. So I'll just say z is just a function of big Z, and that's because we want that plane section remains plane. It's not because of axisymmetry, it is because we want plane section remaining plane. Now what about small z depending on big Z? Can that also be said that no, it will not depend on big Z if it has to be axially homogeneous? What do you think? Think of, for example, simple extension of a beam. Simple extension. And this is the Z coordinate, big Z. So when you, let's say, extend by lambda, how are small z and big Z related? Small z will be equal to lambda times big Z, isn't it? If you say small z is independent of big Z, that is just not possible. Even in the reference state, small z is equal to big Z. There will be a dependence on big Z. So having dependence on big Z does not mean it is non-homogeneous, axially non-homogeneous. For small z, having dependence on big Z does not imply axial non-homogeneity, because this is going to happen even in the most trivial condition. When nothing is deforming, small z is going to remain big Z. Right? So small z can be a function of big Z. But what we will say is that the strain, for example, strain remains independent of big Z. Or maybe we say that the derivative is independent of big Z. So at different points, at different cross sections, we see the same rate of change of small z with respect to big Z. And that we'll call axial homogeneity. Okay? So here we are guided by, and why do we say just for the rate? Because the rate will ensure, having same rate will ensure that it has the same stress components for every cross sections. So that's sort of, axial homogeneity, that the stress components are not functions of big Z. So we are now going to, we forgot about kinematics. Till now we're just talking about kinematics. What about small r, small theta, and small z? But when we came to small z and about axial homogeneity, we see that we cannot get rid of the dependence on big Z, even for the trivial case. So then we say that because we want to deal with axially homogeneous case, we should certainly want that the stress components are independent of big Z, right? So that can happen if strains are independent of big Z, and strains have derivatives. So therefore I said the derivatives are constant. So I can allow this situation. Okay, so I will just say here linear dependence on big Z. And why is it so? For axially homogeneous strain components. Okay, now let's get back to small theta. So this also means we can finally say it is some lambda times big Z. So small z is completely known to us up to this parameter lambda. The function small z is completely known to us up to this parameter lambda. Okay. The function small r is not known to us. All that we know that it's a function of big R, but what kind of function, that is not known to us. Let us get back to small theta. So just like for small z, we cannot forget about its dependence on big Z. Similarly, for small theta also, it will at least be a function of big theta. If nothing is happening, a point, if nothing is happening, a point in a cross section having coordinate big theta will still have the same coordinate big theta, right? So here we cannot say that it will not depend on big theta. In the trivial state also, it has to depend on big theta. So that is certainly going to remain. Okay? But then we'll say that its change with Z is constant. And this is motivated by the fact of what happens when you twist a beam. Can you see what happens when you twist it? The cross sections rotate, but they rotate linearly. For example, you think of a beam which is clamped at one end and you are rotating here by big theta naught. Then here the rotation is 0 and here it is big theta naught. So it varies linearly. It starts from 0 and ramps up to big theta naught. And the rate at which it is rotating, that is called twist, isn't it? You must have learned in your strength of materials class. So we want to keep that here, and I'll say that twist is denoted by, let us say, kappa into big Z. So this is the function for small theta. Okay, so function small theta is also known up to this constant kappa, whereas function small z is also known just up to this parameter lambda. But for small r, it is some function of big R. And we can say that it will be equal to the original big R plus something, isn't it? And let us model it in the following way. Big R into 1 plus, let's say, small b into big R. So this is small b. So this is a function of big R. Okay, so this also implies your UR, the radial displacement UR, is equal to big R into small b of big R. Yes, please go ahead.
So in UV uh, twist and Z, uh,
Yeah.
theta and Z, they were linear because it was assumed that it was small.
Well, not because there the displacements were assumed linear in Z, because this twist was small Therefore, we had assumed the displacement u theta to be linear in z. Here we are not talking of displacement u theta to be linear in z. We are saying, so here this kappa can be finite, this twist can be finite here. And due to this, u theta will not be linear in z. Can you see what will exactly be u theta? Just think of this point, and let us say it is here at big R, and it moves, right? It moves by this angle, which is kappa z due to twist. So it moves and comes over here. Then what is your u theta? So u theta would be this length is u theta.
R tan theta.
No, it is not r times that. R times that is the arc, but u theta is this length. So you see here this u theta is equal to big R into sine of kappa z, isn't it? Sine of kappa z. And this rotation also induces u big R. But u theta is this. And in undergraduate, we assume that this kappa is very, very small, such that kappa into z is also small. And so you could replace this with kappa into big R into z. But here we are not making that assumption. Okay, so this was only in UG course. All right.
Yes, sir.
Okay. So you see, what are our unknowns here then? The unknowns are kappa, lambda, which are just parameters. Or you may have even prescribed it. It may be that you are prescribing kappa and lambda. So it is maybe prescribed or unknown. But this BR, that's a functional unknown, isn't it? So for any functional unknown, you need differential equation. And for simple unknowns, you just need some algebraic equation. That need not be a filled equation. For functional unknown, you need filled equation. You know, some equation which holds in a range, in the range in which this B is present. So we have to think of deriving equations for these unknowns. Okay, so how do we derive it? So of course we know the equilibrium equation, that is divergence of P equal to 0, right? Now as I said, we want to work with cylindrical coordinate system. So we have to think of writing down the components of this equation in cylindrical coordinate system. Okay, so you guys know the cylindrical equation, the Lagrangian form of cylindrical component equation. I think you may not have, many of you may not have seen it. But the way to derive it is very simple. So all that you have to do is, so divergence would be this del over del R of P dot with E big R plus 1 by R del over del big theta of P dot with E big theta plus del by del z of P dot with E big Z. Okay, and taking the derivatives is difficult here. It's not just easy because P you have to expand in cylindrical coordinate system. So you can write as Pij EI tensor product EJ, but I equal to 1 is big R, I equal to 2 means theta, and I equal to 3 means Z. Okay, so the basis, for example, E big R and E big theta, they are also functions of theta. So therefore, you'll also have to take their derivatives. I think I did this sometime. So basically, you'll have to work it out and then finally get it in the component form. And the component form looks the following. Okay, so I'll just write down. So it's a bit bigger expression. So it's del P small r big R over del big R. Okay, so this is PRR component. So this is the Piola-Kirchhoff stress tensor component. So on the radial plane, on the undeformed radial plane, the traction in the radial direction. Okay, so here you have to understand, it is different than what you do in your UG. So Pij, J will denote the plane normal. Whereas this is going to denote the direction of traction. Do you recall in your UG sigma ij, we used to say I is the plane normal and J is the direction. But in nonlinear elasticity for P or for other ones also, the indices have different meaning. The first one is for direction and second one is for plane normal. Okay, and in fact this is more natural choice. Somehow this had been coming and people just follow it in linear elasticity, but this is a more natural choice. And in fact, in my UG solid mechanics course on NPTEL, I also follow this one only, even for sigma. But in most of the books, you will see for sigma, they follow this choice because it has been coming like this. Anyway, so for nonlinear elasticity, the first one is for direction and second one is for the plane normal. So what you have here is this minus P small theta big R. See, smalls are the deformed ones, right? So that they denote the direction. The big ones are the undeformed ones, and they signify the normals, the plane normals. Because P has to, you see, what does it do? If you recall, we said that T naught, that's a referential traction, is equal to big P into E times, or P into big N, where big N was the undeformed normal. So therefore, the second index has to correspond to the undeformed normal. The second index from here. Okay, and then what you get is the referential traction, which has the direction, or which has the actual direction, whatever is the actual traction direction. So what you get from here is sitting in the deformed coordinate system. So therefore, it has mixed indices. One is the deformed one and the other one is the undeformed one. Okay, so anyway, so let me continue with the equation. So you have this, then del small theta over del big R plus P small r big R over big R plus del P small r big theta over R into del big theta. See, all the derivatives will be with respect to undeformed ones because it's a Lagrangian. Minus P small theta big theta by big R into del small theta by del big theta plus del P small r. So this all comes out from here over del big Z minus P small theta big Z into del small theta by del big Z. Okay, and this is equal to 0. So this is the radial equation. Likewise, the theta equation then becomes P small r big R del small theta over del big R plus del P theta R over del R plus P small r theta, which is big theta. Second one is always big one, the undeformed one, okay? Into del small theta over del big theta plus P small theta big R over big R plus del P small theta big theta over big R del big theta plus del P small theta big Z over del big Z plus P small r big Z into del theta over del big Z. So if you have any confusion, please feel free to ask me. I may be, missing out several things, or I may be assuming several things. So please ask me. So this is the theta equation. And finally the Z equation.
Sir,
Yes.
sir, I'm not getting it. What is happening?
See, I'm just writing down the divergence of P in the component form, but in cylindrical coordinate system. Do you remember when you expand divergence of P in Cartesian coordinate system, then what you get? Or at least for divergence of sigma, let us say, what were you getting? You are getting del sigma
Del
xx
sigma
over del x
xx del x
plus
plus
del
del sigma.
tau xy over del y plus del tau xz over del z plus rho naught bx is equal to rho naught ax. Remember?
Yes, sir.
This is the expansion of this divergence in Cartesian coordinate system. I am doing the same thing here, but for the Lagrangian equation and in cylindrical coordinate system. So it gets extra terms. So for example, this is the extra term, this is the extra term, this is the extra term, this is the extra term. These are the usual terms, the derivatives. But you also get extra terms here because the basis vectors are also changing with point. In Cartesian coordinate system, E1, E2, E3, they do not change. Therefore, you don't have to take their derivative. But here, E theta and ER are changing.
Yes, sir. You once did it for one in one question. You showed it.
Okay. Yeah.
Maybe I have to revise it.
Yeah, I just have to go back. But basically, I'm just writing down the equation here, okay? So And then the Z equation is del P Z big R over del big R plus P small z big R over big R plus del P small z big theta over R del big theta plus del P small z big Z over del big Z equal to 0. Okay, this is basically the full derived equation, the expanded equation. This whole thing is that divergence of P equal to 0. Such a big one, isn't it? Okay, now you see, because of the kinematics that we have chosen, that it is axisymmetric, isn't it? When you work out the stress, so with that kinematics, let me also write it only. So our kinematics is, we had that equation, no, for small r, small theta, and small z. So the deformed position is small x as a function of big X, right? This is what we do, no, for kinematics. So here in cylindrical coordinate system, we will say it is small r, e small r, plus z e small z. So this is the position vector of any point in cylindrical coordinate system, isn't it? I hope you know this. It just has this e small r and ez component. There is no e theta component. For example, just think of, any point on this, say this is er e theta. So any point here, what is its position vector? It is simply small r e small r. It does not have any e theta. Any point can be written as small r e small r, any point. Where is theta dependence hidden? It is hidden in e small r. So e small r is a function of theta, because for different theta, the er is going to point in different direction. Okay, so I can make that explicit here. This e small r is a function of small theta. All right. Now with this kinematics and what we just did above, we were saying that small r is equal to big R into 1 plus small b, which is a function of big R. And that small theta is equal to big theta plus kappa into big Z. And small z is equal to lambda into big Z. Okay? So this will, this will also mean that E small r is equal to some rotation big R into E big R. See, because any point is simply rotating by kappa z, isn't it? Any point, because of the twisting, all the points are rotating by kappa z. So therefore, the deformed radial direction E small r and E big R will be related through that rotation. So this big R is rotation about E big Z by small kappa into big Z, which is basically twisting rotation. Likewise, E small theta will be equal to big R into E big theta, and E small z will be equal to E big Z. That's because the rotation is about Z axis only. So E small z and E big Z remain the same. Okay. So the kinematics can also be written as, so small x as a function of big R, big theta, big Z can be written as small r into that rotation big R, and maybe for small r I'll write whatever it is, big R into 1 plus b of big R, okay, into e small r, which is the rotation big R, into e big R, and e big R is now function of this big theta, so I'm making that explicit here. Okay, so the small bracket is to denote that it's a function, so I'll make this big bracket so that you don't confuse here. Big bracket is not for function, small bracket is to denote that this is some function, plus small z, we know it is lambda times big Z, e big Z. Okay, so here is your kinematics fully prescribed in terms of big R, big theta, and big Z. So the deformation gradient will then be del small x by del big R tensor product E big R plus del small x by del big theta, and then you have 1 by R tensor product E big theta plus del small x by del big Z tensor product E big Z. Okay, and when you work out the deformation gradient with this small x written here, what you will get is the following: 1 plus b prime into big R of E small r tensor product E big R. Okay, then plus 1 plus b E small theta tensor product E big theta plus lambda E small z टेंसर प्रोडक्ट E बिग Z, ये देखो सिंपली इसका जब डेरिवेटिव लोगे तो ये आ जाएगा, प्लस कापा बिग R 1 plus b, and then you have E small theta tensor product E big Z. Okay, that's your deformation gradient tensor. And when you express this deformation gradient tensor in a mixed coordinate system, okay, so that this is really interesting here. Till now we had expressed tensor in one coordinate system, but here we are using two coordinate system. For these ones, if we use deformed ER, E theta, EZ, so I'll write here first index deformed E small r, E small theta, E small z, and second index undeformed. So you can also do that, So for each of the tensor directions or each of the tensor vectors, you can use a different coordinate system. So for all of them, it need not be the same coordinate system. So this is called mixed representation.
Sir,
Yes.
so when we wrote del x by del r,
Huh.
so e small r, we did not write it as capital R, E capital R. मतलब 1 plus b dash r.
Yeah, right. So when you work this out, so because you just have to take the derivative with respect to big R, no? So let me just work it out and show you what you get. So this one, for example, when you work out, so we just have to take derivative with respect to big R, okay? And this rotation tensor is not a function of big R, it's only a function of kappa Z. Similarly, this E big R is only a function of big theta, so they are going to act as a constant. So what you get is, you only have to take the derivative of this quantity, which will give you 1 plus b prime R into big R E big R, which is same as 1 plus b prime R into E small r. And that's what I wrote here. Okay?
Yes, sir. So then, how del x by del theta?
This one? Okay. So this one, you have to
Yes,
see
sir.
what is the function of theta here. It is just this one, which is a function of theta, right? Now you may recall del E big
Yes.
R by del big theta. What was that equal to? So that was equal to E big theta. So del E big R by del big theta, that's equal to E big theta. You can go back and see. And del E theta by del theta, that's equal to minus of E big R. So when you work out this derivative, everything is constant except for E big R, right? Which will change to this one, E big theta, isn't it? So what you get is R into 1 plus B into big R into E big theta, which is same as R into 1 plus B into E small theta. Okay, and this is what you see here. You have to also divide by R, no, big R. So this goes away. And you just get 1 plus B E small theta.
And del x by del z may we get two terms because r is a function of z and lambda z
Yes,
ez.
exactly. So that is the most tricky one. This one from here, which is this term here, and the other one is from here, because your rotation is also a function of, it's kappa z, no? Rotation has got that kappa z. So that carves out this term over here. Okay?
Rotation, we how will we write it will be e to the exponential of kappa z.
Yeah, rotation is a function of kappa z, right?
Yeah, so when we take the derivative, it will be of exponential of kappa z.
Okay, let me show you. So this is del big R by del big Z. So this is same as del big R by del big Z into big R transpose into big R, isn't it? Which is, and this thing will give you a skew symmetric matrix. Okay, let us say big omega, a skew symmetric into big R. And this will be such that its axial vector is small omega, that will have kappa into E big Z, the axial vector is small omega. You have to work it out and you will see that you will get it. Okay? So
Okay,
just
sir.
work it out and you will see it. I mean, this is not the, I mean, of course, I should have also completely derived it, but it will take some time. Anyway, once you do this and you try to express this big F in this mixed coordinate system, then the matrix that you get will simply be 1 plus B prime big R, and here you'll have 1 plus B, Here you get 0, 0, 0, 0, 0. Here you have lambda. And then here you have kappa big R 1 plus P. And this is your F small r big R. This is your F small theta big theta. And that's your F small theta big Z. And this is your F small z big Z. And you see we have to use small and big because it is expressed in that mixed coordinate system. And your P, for the P small r big R, will be del W over del big F small r big R. Similarly, P, let's say small theta big Z will be del W over del big F small theta big Z. Okay? What is to be noticed here is that big F small r big theta is equal to big F small r big Z is equal to big F small theta big R, and that's equal to big F small z big R is equal to big F small z big theta, and they are all 0. Right? There are 5 zeros. And certainly this does not mean that del W by del big F R theta will also be equal to 0. So this is not correct. Just because FR theta is 0, that does not mean its derivative will be 0. Because W depends on all the components, no? So after taking the derivative, you have to evaluate it by putting in all the components, but other components are not 0, so you can't say that this will be 0. Okay, so anyways, so coming back to the equation, can you see that as per our kinematics, the only field unknown is a small b. That's the only unknown. But you have 3 field equations present here for radial, for theta, and for z. So it turns out 2 of them get trivially satisfied. The theta and z equations get trivially satisfied. And that's also the landmark or the trademark of this axial homogeneity and axisymmetric case. If you work with axisymmetric deformation, the theta equation will get automatically satisfied. If you work with axially homogeneous deformation, then the z equation will get trivially satisfied. Can we prove that indeed that is going to be the case? Let us try to prove it, okay? So let me write down, or maybe just look at this equation here itself. So what will be this thing? Del small theta by del big theta. As per our kinematics, what is this going to be? Look at the kinematics. So here is this small theta big theta. What will be del small theta by del big theta? Any idea? Anyone? Pulkit, what will be del small theta by del big theta?
That should be 1, I think.
Yeah, it is 1, of course. Similarly, what is del small theta by del big Z?
Kappa. Kappa.
Kappa. Del small z by del big Z, it is lambda.
Lambda.
So those things are required in the equation. So for our kinematics, what is this thing? So small theta was big theta plus kappa into big Z. So this is 0, isn't it? So this goes away. This is equal to 1. this is equal to kappa, right? Then this is equal to 0, this is equal to 1, then this is equal to kappa. Okay, then coming to the Z equation, okay, there are no such derivatives, but then we think of axisymmetry now. So what the axisymmetry and axial homogeneity, what does this mean? That the stress components will not be functions of either big theta or big Z, isn't it? So because of axisymmetry, there will be no dependence on big theta. So all the derivatives with respect to big theta are going to vanish. So wherever you see with respect to big theta, they have to be 0. Anywhere else? Yeah, here. Similarly, with respect to big Z, all the stress components with respect to big Z will be 0. So this one goes away. Then this one also goes away. Then this one also goes away. Okay, so you can see that the equations are getting quite simple. See, this would not have happened if you had used Cartesian coordinate system. So, one of you have to tell me what remains. Oh, okay, I think you will also have a problem, no? Because if I change the screen, you won't be able to see it. So it is this, then this, and the last one. Okay, maybe I will remember. So the radial equation, for example, reduces to del P small r big R by del R plus P small r big R minus P small theta big theta divided by big R minus kappa P small theta big Z. That's equal to 0. So this is what the equation remains finally. Okay. Okay, I think I have this minus sign also present there. Or is this correct? Maybe it is correct. Sorry. Yeah, this is correct. Okay. Then for the theta equation, have a look at this. So theta equation has got this component, this component. Okay, that's difficult to remember. Okay, so it has both of them. And this one. So you have to help me here. So it is del P theta big R over del big R plus P small theta big R plus P small r big theta over big R. What else? The last one, that is P small r big Z. Okay, then the Z equation. Okay, that's not hard. Del P small z big R over del Z is P small z big R. Sorry, this is with respect to R. Okay, so this is what remains finally. But still you see that theta and Z equations are still there. It is not getting satisfied trivially, isn't it?
सर सेकंड इक्वेशन में लास्ट टर्म में कापा भी होगा ना, कापा पी आर जेड.
Oh, okay, I have missed that kappa. Okay. Yes, any more?
Hello, sir.
Yeah.
Sir, I had a doubt regarding using the mixed indices that
Yeah.
this equation, we got it from the LMB, right? The simplified LMB.
Exactly.
So there, when we are using, you told that I equal to 1, 2, 3 become capital R, capital theta, capital Z. And
Okay. So I was wrong there. Thank you for pointing it. It's not really that. Where did I say that? Okay. So, okay. So I think I should use, I have to change it now. So let me use, different indices here. So small I, but I'll say big J. And so these are all big J. But for small I equal to 1, it is small r. Small I equal to 2, it is small theta. And small I equal to 3 is a small z. Because I have to, expand it in the mixed coordinate system, right?
sir, hello.
Yeah, not Niranjana?
Yes, sir. So you have told that the J is the plane normal and I is the direction of traction. So that's why
Yes,
we took as small because it's the
yes,
deformed configuration.
yes.
Oh, okay, sir. This thing was not adding up there. That's why I asked.
Okay. Now, can you think of how can these two equations be trivially satisfied? Well, it should be. If it is not satisfied, then our unknowns must be three filled unknowns. But we have just one filled unknown, that is B. So the remaining two filled equations have to be trivially satisfied. Now, what do you think? How can it be trivially satisfied? Any idea? So must be that the stress components which are involved there, what if they are zero? In that case, it will be trivially satisfied, right? But then how can we force the stress components to be zero? Because they come from the constitutive relation, isn't it? But I will show that for an arbitrary constitutive relation, in the next class I will show you, for an arbitrary constitutive relation, when you evaluate the derivative at the big F that we have just found out, for this particular big F, when you evaluate del W by del F and put in big F this one, you will see that these stress components indeed automatically become zero. And that's how the theta and z equation get trivially satisfied, as it should. And then you will have only one equation remaining. Okay, which you have to use for solving small b. So I will do it in the next class and many more things. But if you have any question from what we have learned today, please feel free to ask me.
Sir, I have one question, but related to, I have gone through the copies of the assignment which you have posted. So
Yes.
in one of the copies you have written that derivative of Eij with respect to Emn, it is equal to delta Im delta In. It is not equal to that because E is symmetric.
Yes, that is true, because you see Eij is same as Eji, no? So even if you are taking derivative of E12 with respect to E21, that's also should be equal to 1, right?
Okay.
But that formula, it will not come out to be 1. So for
Okay.
symmetric tensors, the derivatives are worked out in a slightly different way. And this has been very well discussed in Abhay Ratne's one of the problems. I can point that to you guys, which problem is that, but it is very well discussed in that problem.
Okay, so same will go for skew symmetric also, I think.
Same with?
Skew symmetric because it will become -1.
Yeah, yes. See, so many of you have done this mistake. I don't know where did you get it from. So you had, while finding out the Biot stress tensor, Niranjana also had this mistake. and many more, 3-4 students more, that you got this term like trace of a symmetric tensor. So you had a symmetric tensor multiplied by a skew symmetric tensor, and you had to take the trace of it. So suppose A is a symmetric tensor and B is the skew symmetric tensor. So you had trace of A into B. So what you guys are saying that A into B is a skew symmetric tensor, but it is not. If A is symmetric and B is skew symmetric, that doesn't mean A into B is skew symmetric. And then therefore you say that because AB is skew symmetric, therefore its trace will vanish. So the reasoning is incorrect. Although your final answer is correct, the trace of A into B, if A is symmetric and B is skew symmetric, will be 0. That you can prove using index notation. For that, you don't have to force that A into B become skew symmetric, which will not be.
Suppose we have an arbitrary matrix.
Yes.
So, like, can we always say like, means we don't know whether it is skew symmetric or symmetric, an arbitrary matrix is there. So,
Yes.
can we always say that derivative of Eij with respect to Emn is equal to delta Im delta Jn?
Yes, if it's an arbitrary matrix, then we can say it. If the components are all independent of each other, then of course we can say it.
So then it should be for skew symmetric matrix also, or symmetric matrix also.
No, because for symmetric, the components are not independent of each other, no? Aij is same as Aji.
So what is independence?
Independence meaning if you change one, the other does not change. The derivative should be 0. That is independence. Derivative of one with respect to other is 0. That's the independence.
Okay, sir.
Yeah.
Hello, sir.
Yeah. Yes.
Yes, sir. So in the last question of assignment, I had the doubt like my approach was really short, but I forwarded you the textbook in which I got this approach. So in that they
You see, in
had
the last problem that you have done, I'll actually write you back in a more detailed way. But I saw that you had sigma ij equal toCijkl epsilon kl, and then you are directly writing that sigma ij equal to lambda times trace of this into delta ij. So how did you get that directly from sigma ij equal toCijkl epsilon kl? How do you get that?
we derived in class, right, for the linear
No,
isotropic. So that
we did not derive it. We simply use that.
oh sorry, sir. I
Right?
thought derived it.
Yeah,
Okay.
but the way Purjit has done it, and that's what I also wanted you guys to do, that you start with the non-linear energy form, isotropic energy form, and then you linearize it and show that indeed it gets only two constants. So this is a different proof. There is also another proof in which you start with sigma ij equal toCijkl epsilon kl, and then using the material symmetry, you can show thatCijkl will have a specific form which will have only three constants. So for any isotropic fourth order tensor will have three constants. That's what one has to prove, and use that form in terms of in place ofCijkl, and then when you multiply with epsilon kl, you finally see that those three constants reduce to two constants. But this requires you to prove thatCijkl will have, I mean, what is the form of an isotropic fourth order tensor? That you have to prove. So that's another way to do it.
Sir,
Huh?
the last question, sir, of the previous assignment.
Yeah.
Uh, so I basically got confused that we cannot write function phi in terms of the invariance of E.
Okay. Oh, okay. Yeah. See, yeah, I see what you had done. So basically.
So it was wrong. Mine was completely wrong. I agree, but
Oh,
I'm
sorry.
just asking.
Yeah, because you see that those scalar functions are functions of the invariants of C, right? So you cannot directly say that, okay, so it also can be alternately written as functions of invariants of E. For that, you have to show that IC, 2C, 3C can be written in terms of IE, 2E, 3E. And that's not trivial. You can do it for IC, for example. IC is trace of C, which is same as 3 plus 2 times trace of E. So IC can be written in terms of trace of E. Likewise, 2C also you can show it can be written in terms of IE and 2E. But 3C, I think you'll have hard time showing that you can write it in terms of 3E or the combinations of it. So that's something you had to, if it can be done, then you had to prove it. But I think perhaps it's not possible also.
So if it were possible, then I would have gotten the correct answer.
Yes, exactly. If it were possible.
So CIJKL, it is a symmetric fourth order tensor, and in the last class we proved that it is equal to a del of sigma and with respect to del f at f is equal to I.
You mean, yeah, yes. So C as identity, which by definition is del of P with respect to del F at I, is also equal to del of sigma with respect to del F at I. Yes.
So my question is that sigma is symmetric,
Yes.
and and f need not be symmetric. So
Yes.
so but CIJKL turns out to be symmetric.
No, symmetric in what? So CIJKL is same as CKLIJ. That is from the definition of CIJKL. And then CIJKL is equal to CJIKL, but only at in the reference state. And that's because you could show that it is also equal to del sigma ij over del FKL. And sigma ij is same as sigma ji. So the elasticity tensor in the reference state has got this extra symmetry that Cijkl is equal to Cjikl.
Sir, wasn't it CKLJI? CIJKL is equal to CKLJI.
Well, that's also obvious. So if Cijkl is equal to Cjikl, then you
Okay,
also flip
you
the
should.
first two and last two, and you get what you are just saying.
Okay.
Yeah.
So in fourth order tensors, there are many kinds of symmetries.
Yeah, of course.
So, sir.
Yeah.
So, we are taking the derivative of sigma with respect to f, and uh, uh, to take the derivative, we will scalarize it.
Yeah.
And then then since we are doing it for sigma, so sigma is symmetric. That tells us CIJK is symmetric.
Again, don't say Cijkl symmetry. You have to say in which symmetry. So you mean Cijkl equal to Cjkl, right?
Oh, okay, sir.
Yeah. That saying symmetric is vague. You have to say in what indices. What indices when you flip, you get the same thing. Because there are 4 indices, right? It's not like a second order tensor which has only 2 indices. Then symmetry is very unique that Aij equal to Aji. But here you have 4 indices. So you have to say precisely what symmetry you are talking about. Okay. Any more question? So if not, then I'll meet you guys on Monday, and wish you a very, very happy New Year. Okay, enjoy the time.